got stopped in the previous lecture, so let us continue from where we left. Okay, so in z direction, del p by del z plus rho into bz is equal to rho into az. This was the equation. So minus del p by del z plus rho into body force per unit mass is given by, in the z direction, is given by mass into acceleration due to gravity divided by mass, but acceleration due to gravity is acting in the negative z direction, so this is given by minus g because we have taken z to be in the positive direction. This you have to keep it in mind. Okay, is equal to, it is, we are assuming there is no any kind of acceleration in the z direction, so the right hand side comes out to be equal to 0. Now del p by del z is equal to minus rho g. So dp is equal to rho into minus rho into g into dz. Now integration will give dp, integration from p1 to p2 will give minus of rho into g into integral of dg from g1 to g2. Okay, now p2 minus p1 comes out to be equal to minus rho g into z2 minus g1. Okay, g2 minus g1. Now what I can say, p2 is equal to p1 minus rho into g into g2 minus g1. So g2 minus g1 is something which is positive because we are considering z to be positive in the upper direction and z1 is lesser compared to that of z2, so this is positive, and we are subtracting something from p1, so p2 is of course less than p1. This implies that if we are moving in upward direction, in that case what we will see, the pressure gets reduced by rho into g into height at which we have traveled in the upward direction. Okay, the similar equation can be written as p1 is equal to p2 plus rho into g into z2 minus z1. This is the another form of writing. In this, from this equation you can say that if I am at a particular height and the pressure at that point is known, and if I move downwards, then in that case this pressure will increase, and it is increased by rho into g into h. Okay, so you can see that pressure at any point is written with respect to the other pressure, like pressure at point 2 is written with respect to p1, how it is less than or greater than p1, or pressure at point p1 is written with respect to pressure p2. So I can say that pressure is expressed in reference pressure. Pressure is expressed in terms of reference of some pressure. Okay, pressure expressed in reference of some pressure. This is the first point. And if the reference pressure is atmospheric pressure, then pressure is called gauge pressure or gauge pressure. It's called gauge pressure. With respect to atmospheric pressure means that how much it is above atmospheric pressure. So if I have to write P1 with respect to P2, then I have to say it is rho into g into z2 minus z1, means with respect to P2 how much it is above P1, how much it is above P2. Okay, so in that case I have to say that with respect to P2, the P1 is equal to rho into g into z2 minus z1. So if P2 is equal to atmospheric pressure, P1 becomes equal to gauge pressure. Okay, so this is something. And if the pressure is less than atmospheric pressure, then, or less than, like in the first equation, in this equation you can see in this equation, P2 is equal to P1 minus rho into G into Z2 minus Z1. So it means that pressure P2 is with respect to P1 is minus into rho G into Z2 minus Z1, means it is less than P1. With respect to P1 it is negative, means it is less than P1. Okay. Now we would like to move forward and we would like to solve a problem on variable, and which is closely linked with what we have discussed till now, how pressure is varying as we are moving up, we are moving down. So let us try to solve the problem. Okay, it is a variable problem. So I have a gate, left side of which is filled with water or some kind of liquid. This is filled with some kind of liquid, height of which is given by capital H. Okay, and I have some gate here whose radius is given by r, and it is circular, and the circle is perpendicular, semicircular, and the semicircle is perpendicular to the plane of sheet on which I am writing. Okay, if I want to show you how it looks like from a person standing here in the water, standing here in the water like here, and he is looking in this direction, how it looks like is given by, I will draw it here. Okay, this something looks like, it will something look like this. Okay, this is the way this radius becomes equal to r, and you have to find how much of torque is required to keep this gate in position, because liquid is filled from this surface to this bottom, so as we are decreasing to the height, if suppose this is the positive z direction and the below is the negative z direction, so as we are decreasing from a certain point, suppose this is PATM, and we are measuring the pressure at any point with respect to PATM, so the pressure here at any point like here is increasing as a function of, as we are decreasing from top to the bottom. Pressure at this location, let us say, is P1, then pressure here will be furthermore, and it is given by P2, and as we reach at the bottom, the pressure is furthermore, and it is given by Pn. Let us say Pn. P1 is smallest, P2 is larger, and Pn is further very large. So because of, I have not drawn this, let us, okay, let us draw it from this side, because in this side liquid is filled. P1 is smaller, P2 is larger, and Pn is further very large. Okay, this is P1, this is P2, and this is Pn, and it is magnitude is governed by the equation rho into G into height. Okay, so because of the action of the force on this plate, because up to this height we have a plate of radius r, it will try to rotate this plate in this direction. This would be the water will try to rotate the plate like this. So I have to put a force F in order to maintain the torque which is generated by the different forces which is acting due to the liquid which is present in the left side. So how much is that torque, this we require to calculate. Okay, so this is a very interesting problem which we would like to discuss. Let us say I try to copy this, and using this we will do our analysis. So let us move on to solution, and we just need to find out what is the total amount of torque which is required to keep the gate in position. So let me paste this. Okay, so this is the semicircle. So this is a variable problem. I would like to solve this problem by approach, and you will just see, suppose at any angle theta we have a small angle d theta, and at a distance r we have a small length dr. So we have taken this as a element whose length is given by dr, and the small angle is given by d theta. Okay, now I just want to evaluate at what depth from the top it is located, because if I would be able to know the depth at which it is located from the free surface, I would be able to calculate the area, I will be able to calculate the pressure at this point. and if I multiply this pressure with the area which is associated with the small element, I will be able to calculate the force, and integrating that force from for theta and r, we can get the entire force which is acting on this surface, or we can get the torque as well. So let us try to find at which height it is located, or sorry, at which depth it is located from the free surface. So the from the very top, this is located at a height, at a depth h, capital H, because the depth of the liquid is h, capital H. Now let me again draw this. Okay, let me again draw this. And this radius is given by capital R. We have taken this element. So this is a differential element which has a angle d theta, and it is a the length of this is given by dr. So if I want to find what is the height of this particular element from the bottom, I want to try find what is the height, because I know the depth of the bottom. If I will be able to find the height, this particular h, this is theta, then I would be able to find the depth of this element. Okay, so let me this is capital H, this from the top it is capital H, this bottom is located at a capital H depth. So what is sine theta? This is small r. At a small r distance I have taken dr. Sine theta is equal to h divided by capital R. Okay, so h is given by r sine theta. So the depth is given by capital H minus small h of the element that I have chosen. This element that I have chosen, which is marked in red. For that, capital H minus small h is given by capital H minus r sine theta. Capital H is known to me, r is a variable, theta is a variable. Okay, so this is something which we have obtained. This is the first equation. Now I want to find what is the pressure acting at a height, at a depth capital H minus small h from the top. So what is the rho into g into, what is the pressure acting? Rho into g into capital H minus small h. Small h is given by r sine theta, so r sine theta. This is the pressure. What is the area? Because pressure when gets multiplied with area will give the force. Area is given by r into d theta into dr. Because I have taken an element, such kind of element, this is radial and this is something, so this approximately is equal to this, because it is a differential element, and it is given by r into d theta at whatever radius I have taken. So this is r, then this becomes equal to r d theta, and this also becomes equal to r d theta. And what is the length of this? This is dr. So what is the area of this element? Is given by r dr d theta. Okay, that is what I am writing. So this is the total force, and multiplied with what is the r cross f. If I have to take r cross f, then magnitude is given by r into f into sine theta, and sine theta is always equal to 1, so I will multiply it with r, and sine theta is equal to 1, so 1 need not be multiplied. So this gives me the total amount of torque which is associated with a very small element which we have taken. All right, so rho into, so what is the total m is given by rho into integral of rho into g into h minus r sine theta into r square dr and d theta. The integral is for both dr and d theta, for variable theta and r. Theta when integrated from 0 to pi will give me such a slice, something like this. So I will be able to find what is the torque acting due to this slice, and when it is integrated from for r it will be integrated for 0 to r. So if I will integrate all these elements from 0 to r, I will be able to get what is the total amount of torque which is really acting. So if you will integrate this, what you will get is rho into g into h into so multiply this. If you will multiply this, rho into g into r square into dr into d theta minus rho into g into r cube into sine theta dr d theta. The integral will act on both, and the limit will be 0 to pi and 0 to r. Just by a simple integration, here r is function of r square is function of dr, and d theta gets integrated, it will give 0 to pi. And for the second function, r cube is integrated with respect to dr, it will give r to the power 4 divided by 4, and the integral of sine theta from 0 to pi will give 2. So it is very simple integration which you can do in order to find what is the total torque acting. So now what is the total torque acting is known to me. So force into r, because the force which is acting is force is acting at a radius r, okay, or at a height r from the bottom. In that case, what is the total amount of total magnitude of torque acting? Force into r into sine theta. The there the angle between force and vector r is equal to 90 degree, because of which the magnitude becomes equal to force into r into sine theta, where theta is equal to 90 degree, becomes equal to force into radius, and it becomes equal to the total amount of torque that we have generated. So from here, if I know m, so F must be equal to m by r. This is the total amount of force which is required to be applied at a point which we have located in this figure. This is force acting. Okay, so the opposing forces will balance the torque about the moment. Opposing forces will balance the moment about the axis. Okay, now moving on to the next topic, in which we want to discuss what is the force on curved surface. Force on the curved surface. Okay, so many times I feel that sometimes I do struggle to convey any concept to you, but I think if you will uh, just rewind and again go through the fact what I want to convey, you will be able to get what information I want to convey to you. Okay, so I'm first time taking the lecture, so it may happen that sometimes I may not be able to convey what I want to. Okay, so just try to repeat and you will be able to get. This is the control. This is the surface. This is the surface, or let me draw it with the different color. This is the surface. This is the surface which is kept in some kind of liquid. This is the liquid, and suppose I draw a control volume, something like this. This is the control volume, and I want to evaluate what is the total amount of horizontal and what is the total amount of vertical forces which are acting on this plate. This plate, note that this plate is a curved plate, and it is extended perpendicular to the seat on which I am writing. Okay, so if ABCD is the control volume, ABCD is the control volume. So let us try to find what are the different forces which are acting on the control volume. So from the left side, let us suppose horizontal force FH1 will be acting on the left face. Suppose on the right face, the force acting is FH2. From the body force, you can say weight is acting in the downward direction. And due to the presence of plate, suppose the plate exerts some kind of force in vertical direction, which is given by force Fv. This is given by Fv, and due to the plate, the force is acting somewhere in this direction on this control volume that I have taken. So suppose this is given by Fh. Now I would like to balance all the forces in all x and y direction. So let us first try to balance the force in horizontal direction. Force balance in horizontal direction. So what is force acting in the horizontal direction? The first force which is acting, force balance in horizontal direction, is given by summation of all forces equal to mass into acceleration. The acceleration comes out to be equal to 0 because we are talking about the static fluids. So summation of all forces equal to 0. What is the force acting in the horizontal direction? The first force, suppose taking right hand side to be positive, Fh1, suppose this is our coordinate system, this is x, this is y, this is y. Okay, Fh1 is given by is positive sign and minus Fh2. Fh2 is given by negative sign and minus Fh is equal to mass into acceleration is 0, so it comes out to be equal to 0. So what is Fh? Fh comes out to be equal to Fh1 minus Fh2. Alright, Fh1 minus Fh2. So Fh is the total force which is exerted by the plate on the control volume. So from the Newton's third law of motion, since since plate is exerting a force of Fh in the horizontal direction on the control volume, so the same amount of force will be exerted by the control volume on the plate, but the direction will be reversed. So what is the force? This is force exerted by plate, curved plate or curved surface in horizontal direction on control volume ABCD, because we have written the force balance on ABCD. So whatever force is acting on control volume ABCD. This implies that force applied by control volume on curved surface AD is equal and opposite, and it is given by minus Fh. It is given by f of h2 minus f of h1. Alright, sorry, f of h1. So we have found that what is the force which is acting in the horizontal direction on a curved surface if fluid is present above it. So we will draw a control volume extending up to the surface, and we will find what is the force acting in the h1 direction and what is the force acting in the h2 direction. We will take the difference of f of h2 minus f of h1. It will give kind of horizontal force which is acting on the curved surface by the fluid which is present over it. Okay, now this is the first analysis. This is the force balance in horizontal direction. The second is force balance in vertical direction. Force balance in vertical direction. So what is the total amount of force which is exerted by the fluid in vertical direction? Sorry, what is the total amount of force which is exerted on control volume ABCD in the vertical direction? The first is, or you can write summation of all forces in y direction is equal to mass into acceleration in y direction. We are considering the static fluid, so because of that, mass into acceleration AY comes out to be equal to 0. So summation of all forces in y direction comes out to be equal to 0. The first force which is acting is Fv, and it is taken as positive because y axis we are taking it positive in upward direction, and minus W is equal to 0. So force in vertical direction is equal to W. So what is the force exerted? Force exerted by the curved surface on control volume ABCD is equal to W, or weight of the liquid. Weight of liquid above it. Weight of liquid above it means if I am drawing from the one edge a line or a surface extending all the way up to the open atmosphere, and from the other end of the curved surface all the way up to the point C, or to open atmosphere. So in that case, whatever the total amount of fluid which is collected in the control volume is given by the weight W. The weight of that particular liquid is given by W. So this is the force exerted by the curved surface on control volume ABCD. Control volume ABCD. So what is the force exerted? By control volume on the curved surface is equal to minus W. This is by Newton's third law of motion. Newton's third law of motion, that if a body B1 applies F1 force on another body B2, then body B2 body B2 then body B2 applies equal and opposite force F1 on body B1. Since this control volume and the surface of control volume and the curved surface are in contact with each other, so whatever force, this is control volume, this is curved surface, whatever curved surface force applies on the control volume, suppose in y direction I am saying, whatever force in y direction the curved surface is applying on the control volume, the same amount of force curved surface will apply the same amount of force will be applied by the control volume on the control surface, and it will be given by a negative sign, because curved surface is applying force on control volume in upward direction, whereas the control volume will apply the force on curved surface in the downward direction. So the force which will be acting by the control surface will act on control volume, and the force acted by control volume will act on the control surface. They are not acting on the same bodies, therefore they do not cancel with each other. The force is acted by one body on the different body, and the second body applies the force on the first body. So this is the Newton's second law of motion, by which we can come to the conclusion that if the control volume experiences a force of W, then the force which will be experienced by the control curved surface is given by minus W. Okay, this was the basic detail of what I wanted to give in this lecture. Now we are in position to discuss some problems related to this lecture. The topic that we have covered, force on the curved surface, and you will be very astonished to know that many different integral problems can be made very simple by using this concept of force on the curved surface that we have discussed just now. So in the next class we will take some problems related to the force on curved surface, and we will try to find the solution by using the integration, and very rigorously we will find it, and later we will be just matching the result with whatever concept we have discussed here, and we will try to match those two results, and we will try to see whether the results are matching or not. So for now, let us summarize this lecture, or let us close this lecture at this point, and we will discuss the examples of this particular lecture in the next class. Thank, thank you.